Hi guys, the topic I will discuss is the application of first order ordinary equations ODEs, and the title we choose is Lotka-Volterra Prey-Predator Model. This is the descriptive title of our group. We are group 6 from section 34 from the course of SSCE1793 differential equations. Now let's proceed to the introduction of the topic. So the Lotka-Volterra Predator Prey model was proposed by Alfred James Lotka and also Victor Volterra, and this is a first order nonlinear differential equation. It frequently used to describe the dynamic of biological systems, which is including the relation between prey and predator. Besides, this model also used in economic and marketing areas. What is order differential equation? An order differential equation have one or more than one dependent variable, but only have one independent variable. Therefore, for first order differential equation, it is the order differential equation which have highest derivative of 1. For the example of first order derivative equation, we have linear differential equation, and this is the equation for the linear differential equation. For linear differential equation, it has a dependent variable and derivative with only degree of 1, and for each coefficient only depends on independent variable. This is Lotka-Volterra equations, where x is equal to the number of prey, y is number of predators. dx dt and dy dt is the instantaneous rate of prey and predator respectively. So t will become the time, while alpha, beta, delta, and gamma is the positive real constant, which can be get by the analytic in the real world. So we have a look on the first equation. In this equation, since the coefficient is not depends only on independent variable t, but also depend on x and y, which is the dependent variable, so Lotka-Volterra equation is not linear. This is the graph of population versus time. The prey is denoted by the blue line, while the predator was denoted by the red line. Initially, the number of prey is increasing. So as it rises, the predator also will slowly increase after the prey increase. Later on, since the number of predator increase, the prey as a food will become less and less over the time, so it will start to decrease. As there is lack of food, the predator will also decrease. So after the predator decrease over time until a certain value, there is less predator to catch the prey. Therefore, the prey will slowly increase again, and the loop is starting over again and again. This is the Lotka-Volterra equation plot. The diagram is called as a phase plot. The y-axis is for the number of predator, while the x-axis is for the number of prey. As we recall on the equations, dx dt equal to alpha x minus beta xy, while dy dt equal to delta xy minus gamma y. In this graph, it shows many of closed loop, and for each point on the loop, the t1, t2, t3, and t4 is the specific time in this green loop for the number of prey and predators. From t1, t2, t3 to t4 and then back again to t1 is a closed loop in this green loop, and it shows the change of the number of prey and predators. And then the center here, which is the equilibrium point, and from here the dx dt and dy dt is equal to 0. Therefore, x alpha negative beta y equal to 0, and y delta x minus gamma is also equal to 0. Hence we get that x equal to gamma over delta, y equal to alpha over beta in the equilibrium point, and we assume that x, y not equal to 0. Next problem statement. For the following problem, there are few assumptions. The first one is there is no shortage of food for the prey population. The amount of food supplied to the prey is directly related to the size of the prey population. The rate of change of population is directly proportional to its size. Fourth, the environment is constant and genetic adaptation will be negligible. Predators will never stop eating. This is the example for the Lotka-Volterra equations. We given the constant alpha, beta, delta, and gamma, and also the initial value of y and x. So in this question, what we need to find is yx. Now let's proceed to the problem solution. So first, by substituting the constants alpha, beta, gamma, and delta, we got these two equations, which for the prey and also the predator. Then by using chain rule, we can find the relation between y and x, which prey and predator, by multiplicating these two equations. After that, we got the expression of dy dx. Later on, we use separable equation to solve this, and then we integrate. We got this equation with a constant. So by solving using the initial condition of x0 and y0, we got the value of c. Lastly, the yx is equal to this equation. From the equation, the graph shows the population of prey and predator can be plotted. So after plotting the graph by using the y-axis equation, we got a closed loop, which is same as the previous space plot. So for this loop, it shows the relation between the prey and predator at certain time. In conclusion, the study of first-order ordinary differential equation is fundamental in understanding various natural and engineering systems. The Lotka-Volterra equation offers valuable insight into the dynamic of prey-predator relationship in ecosystem. So through the analysis of these equations, we can know about how the two species population influence each other over time. Furthermore, Lotka-Volterra model exemplifies the power of first-order differential equation in capturing the nature of biotic interaction and predicting future population trend under specific conditions. Therefore, researchers can understand the effect of various factors and find the strategies for conservation and management about endangered species. Last but not least, this assignment allows us to understand how important the application of first-order differential equations is in our life and society. It also emphasizes the significance of differential equations in different scientific and engineering applications, and their role in solving practical problems and improving our understanding of the natural world. In other words, this assignment lets us know that what we learn is meaningful, and it also lets us know the importance of this course being listed as a required course in engineering courses. Last but not least, this is the reference. Thank you.